really excited to do this panel and to have such great guests. So first, I'm Eike Langbehn. I'm still connected with the University of Hamburg, but I also co-founded a company called Curvature Games. So say a little bit more in a couple of minutes to this. And I have 5 speakers on this panel with me, which are Mary Whitton from University of North Carolina, Frank Steinicke from University of Hamburg, Evan Suma from University of Minnesota, Eric Hodgson from Miami University, and Keigo Matsumoto from University of Tokyo. And I will just give a short introduction into the topic and show a little bit of my research, and then we will each of the speakers will have 5 minutes to give a short presentation on the research he or she did on redirected walking. And after this, we will have a discussion, and we may also have questions from the audience. Okay, so let me just start with a short introduction into the topic. So we're talking about locomotion and virtual reality, and we all know that there are a lot of different locomotion techniques. For example, there are virtual locomotion techniques like joystick steering and teleportation, but all of them have different drawbacks, like regarding the sense of presence, VR sickness, or spatial knowledge, like disorientation. And it was shown that real walking in VR does not have these problems, but real walking, of course, is just limited by the amount of space that you have in your tracking space. So there are different approaches to overcome this, to use the benefits of real walking without having a large or infinite tracking space. For example, hardware devices, omnidirectional treadmills, but also walking in place. And one of these approaches is redirected walking. And redirected walking started 20 years ago, well, almost 20 years ago. The first paper on this was published in 2001 by Sharif Razak, Mary Whitton. Actually, I don't know the first name of, is it Zachary Cohn?
Zachariah.
Ah, okay, thanks. And I'm very proud that one of the authors is here today, Mary, and I think she will also tell a little bit more about these times back then in a minute. But yeah, since then, a lot of research on this topic was done. And yeah, I just had a quick look on Google Scholar and found like 42,000 results on redirected walking. I'm sure not all of them are like about redirected walking in VR, but still we know that each year at each conference there are some new papers that advance the field. And so I thought it's time to have like this panel to talk about what we did in the past, in the last 20 years, and also like where we are heading in the future regarding redirected walking. Just very shortly about myself. So my first contact with redirected walking was in 2014. I was a master student, and I participated as a subject in a study from Gerd Bruder, who's like the general chair of this conference now. And this was not only the first time I experienced redirected walking, but it was also the first time I wear a head-mounted display at all. And it was a really great experience, both the VR, but also redirected walking. But I got really sick after like 20 or 30 minutes. And had to rest for 1 hour or so. But still, a couple of months later, I became a PhD student myself and did research on redirected walking. For example, I did some work on detection thresholds for bending a curved path that is already curved to find like configurations of different paths to walk infinitely. I did experiments on using transcranial direct current stimulation to manipulate the thresholds, or like being even able to redirect even more. I did some work on eye blinks and using eye blinks for additional redirection. And I also did some more hands-on work, for example, here, where I used a haptic prop and yeah, to show and to illustrate how redirected walking works. So here, the table is used twice. The real table is the same real position, but it's used twice in the application. We have two different virtual tables. Like you can see here. Or another example of some hands-on work is this demo where we used interactive distractors. So the user has to do a task while a rotation gain is applied and the world is rotating around him. And then after I finished my PhD last year, I co-founded a company, Curvature Games, and we are developing VR games. And here you can see a VR experience that we did for theme parks and location-based entertainment. And we also use some redirection techniques in these experiences. You can see it's a two-player experience where two players are in the same tracking space, both redirecting, and we are redirecting both of them at the same time. Okay, and that's from my side, and I would like to, I will stop my share and pass on to Mary.
All right, thank you, Eike. Redirected walking actually goes back on 25 years. Mike Michel and Dane Mapes from University of Central Florida had the idea that you could make somebody walk, I think they were walking straight and walk curved. And they came to Carolina because we happened to have sort of an 8x12 tracking space. It was the predecessor of the highball tracker. They were still eventually stymied by the lack of small tracking space and the fact that, think about the quality of VR systems 25 years ago, and they were terribly sim sickness inducing, slow update rates, low resolution displays, etc. Then in '99, Sharif Razak, independently of Mike and Mapes, came up with the idea of redirected walking, making people think they're walking straight while they're walking a curve. Very much an example of vision dominating vestibular. Sharif had a goal of having the rotation be imperceptible and no increase in sim sickness, he hoped. Sharif had at least 2 psychologists on his committee and ended up, because of that, having really great background sections. And if you've never carefully looked at his whole dissertation, I encourage you to do that. One of the figures that's in there is this one that talks about visual and vestibular contribution. So there's a step function stimulus in the heavy red line. The vestibular inertial is the starting fast, going down quickly, orange line. Visual perception slows up slower, and steady states. And the combined visual perception, you notice, becomes very, very dominated by vision once time gets out further past the stimulus. So another way to look at that is sensitivity to motion. So the horizontal axis now is the frequency. It happens to be an angular velocity. And when the angular velocity is low, visual sense dominates. When it's high, the vestibular dominates. So when we're doing redirected walking and rotating the world around you, what we want is you not to notice it visually, but so we need to stimulate the vestibular. So let's look at how that got implemented in Sharif's work. Boy, this is a classic picture. And I think it's, just remember that the red outline is the space of our lab at that point in the tracked space, and the blue was the virtual. It was really great the first time we plotted this and realized, wow, this really works. But how did Sharif get you to move your head? So how did he elicit the head turns to reduce the visual perception of the rotation? There are two two ways you can do this. One is to contrive or design the scenario so that you force the head turns, and that's what Sharif did. Each time his user got to one of his waypoints with the green arrows, they were instructed to look around to find the next waypoint. This forced them to at least rotate their head once, let them insert enough rotation to get them headed off in the other direction. If you remember in the red figure, the lines were sort of curved, and so there was, while they were walking, there was still some rotation being inserted. So at a contrived environment is one of the ways to force you to move your head. Now, the other person who did a lot of work was Tabitha Peck, our second dissertation in redirected walking. And she introduced the ideas of distractors, where something appears in front of you in the environment, and it goes back and forth around a semicircle and with a sinusoidal speed, and you're instructed to follow it. And while your head is moving, she was able to insert the rotation and get you to turn in the direction that you want. She looked at visual only distractors, at audio only, the hummingbird wings, and at the combined visual and audio, which was what her user subjects preferred. It's a technique that works surprisingly well. Audio was deemed difficult because spatially locating the audio so that you can then begin to know how to turn your head was difficult for the users. It's a good technique because it doesn't require you to change the models or to do anything particularly weird with the models, but just add the distractors to the system as you've got there. The distractors do interrupt the experience. They cause a break in presence. A really bad problem is getting stuck in corners, which some people have adapted by using their boundaries as an oval rather than a rectilinear figure. And at the end, the steer to problem and this choice of where you're going to steer to was still an open question that she didn't address. But we got two really fine ideas. The whole basic idea of redirection and the distractor idea got introduced in our lab. At that point, I went off and did big data for a couple of years, and the locus of redirected walking research pretty much transferred to Frank's lab, and he is the next speaker. And let me unshare if I can figure out where to do that. Oh dear.
Thanks, Mary. I think I can just hand over, and I did already, I think. Okay. So you see my slides?
Yes.
Okay, perfect. So thanks, Mary, and thanks also for starting this amazing research with your group. So when we started to work on redirected walking about 10 years ago, together actually with our general chair, Gerd, and later Eike, we closely cooperated with psychologists. And I would really like to emphasize also this point that Mary made, how important it is to include this perspective when developing perceptually inspired redirected walking. So when moving through the real as well as virtual world nowadays, humans perceive multisensory information about self-motion, and most redirected walking techniques today focus on visual, vestibular, and proprioceptive perception and manipulation. And this multisensory information is combined and integrated to identify self-motion. And there are essentially two models which describe how stimuli from different senses can be combined. And in the maximum likelihood estimation, for instance, each stimuli from the different senses is weighted in the Q integration, and the weights typically specifies the reliability of the individual sense. And in virtual reality, typically vision gets a very high weight and therefore can dominate vestibular and proprioceptive information. So let's have a look how this full perception action loops look like when we walk. So multisensory information, as I just mentioned, is perceived and then typically processed in a bottom-up way, for example, by processing the optic flow information. Cognition interprets this movement, but also affects the perception based on prior experiences or priming, and therefore also influences the perception in a top-down, hypothesis-driven way. Cognition then guides motor action in a top-down way, but again, at the same time, bottom-up revisions regulates the actions. And finally, motor commands are initiated which affect the real or virtual environment. For instance, we move or change our view to the environment. And finally, we can observe the updated internal and external self-motion cues. Typically, redirected walking now changes or manipulates this mapping of motor commands to the virtual environments, for example, by using gains which move the virtual camera differently from the actual head movements. But now at the same time, when the afferent motor commands are sent to the muscles, an afferent copy is used in a forward model to predict actually the sensory feedback. And then a comparator compares the observed feedback with the predicted feedback. And typically there is always some small sensory discrepancy between what was predicted and what was actually observed. And if this discrepancy is small enough, people will not notice and simply adapt their motor control. And the question is, of course, in redirected walking, how much manipulation can we induce in such a way that the sensory discrepancy gets unnoticeable? And the amount of redirected walking manipulations which can be or cannot be noticed can be identified by standard psychophysical methods. And there are several methods to identify absolute and difference thresholds, which show how much deviation between the stimuli gets unnoticed. And here is a video from one of our earlier work, which uses such a psychophysical methods, 2 alternative forced choice tasks, and the graphs, like the one on the bottom right, have been used several times to identify those detection thresholds. And using this methodology from our group, as well as several other colleagues, have used this methodology to identify, for instance, detection thresholds, for example, when working on a curvature. And it's really interesting to see that with improving technology from year to year, the required radius, for example, to guide users on a circular arc, which they perceive to be straight, decreases. So Sharif took about 15 years ago more than 50 meters. In my own work, about 10 years ago, it was still 20 meters. And nowadays we are somehow in the range of 10 meters, which are still required. And here I plotted the required radius for curvature gains to the number of megapixels provided in head-mounted displays nowadays. And though the correlation is not too high, it looks like there is a limit of what we will be able to reach by visual dominance only. And hence it gets important to also use other approaches, and in particular the imperfection of the human information processing. And we have perceptual filtering, for example, in the perceptual part, but also selective attention, and Evan will talk about change blindness and attentional blindness using this limitations of the human perceptual system. Here are just the examples that you already saw from Eike, which show, for example, how we use perceptual filtering, for example, during saccades or blinks, in which a lot of visual information is filtered, and you can use this, for example, to manipulate without users noticing. Here's also the TDCS example you just showed. So here we applied a very weak current to the scalp to manipulate the prefrontal cortex and the parietal cortex, which are both important for spatial navigation. And we have found some significant, but though limited effects, but it's an interesting ongoing direction to better understand the multisensory integration process during redirected walking. And finally, also, this is the video that you saw in Eike's presentation. I think that also the combination of those different tricks, such as gains, impossible spaces, change blindness, might be a good path for future improvement of redirected walking. So that's it from my side, and I hand over to the next speaker.
All right, I think I'm up next here. Are you all able to see this okay, or am I too small on the screen?
I think we need to, everyone needs to pin your video.
Yeah, you need to switch to speaker view in Zoom, or you can pin the video, then it's large.
Okay. Yeah, if it becomes an issue in chat, just let me know and I'll switch over to screen sharing. So I am Eric Hodgson, and I am a cognitive psychologist as well. So my formal training was in spatial perception and navigation and things like that. And these days I teach in emerging technology and computer science. So I kind of run the gamut a little bit. I'm probably best known for my work in the hive. So, as Mary mentioned, one of the big limitations of doing redirected walking research is you need a big space, right? And, Frank brought this up as well. And I've been fortunate enough to have some space available where I can actually work on implementing some of these algorithms and, putting people in environments and just giving them a search task, go wherever you want, do whatever you want to do. And I'm going to try really hard to keep you from hitting the brick walls at the edge of the gym here. So we have about 1,100 square meters of tracking space. It's a 25 meter by 45 meter We can track the whole space and let people walk wirelessly. And a lot of the work I've done over the years really looks at comparing different approaches. So if we steer people to the center, if we steer them to orbit, if we steer them towards waypoints, we've done stuff with path prediction and those kind of things. And just trying to see, you know, which of these ideas really are effective in the real world with real users who are just, you know, kind of wandering aimlessly. There are different classes of algorithms. You know, some are more predictive, some are more reactive. There are a lot of really good techniques that have cropped up over the years, and we haven't been able to test all of them. One of the earliest studies we did in the lab, we put people in a virtual forest. Graphics have improved tremendously over the last decade or so here, but we had people wandering around the forest just kind of collecting posts. And this was kind of a good example of an open world, you know, virtual environment where there's really nothing to constrain the user. You can go wherever you want. You can turn at any time. And, you know, just kind of meander through the trees. And this is actually a really good situation for redirected walking because people are turning constantly and you have a lot of extra rotation that you can amplify. And again, we're able to contain them in the gym while they kind of wander around through the forest there. We've done a lot of other work looking at very highly constrained environments, right? So instead of being able to turn freely, you have to kind of walk up and down aisles. You have 90-degree turns. You can't just go wherever you want. In this case, we gave people a shopping list in the grocery store and had them try to walk through with different algorithms. And generally what we found in most of these studies is that steer to center, which was, I think, Sharif's original implementation, is really kind of one of the best, right? You want people as far away from the walls as possible. You want them kind of in the central area. In highly constrained environments like the grocery store, steer to orbit can work fairly well sometimes because they're doing very long straight paths and you know, large enough turns that you can wrap them around the other direction. But for most environments, steer to center seems to beat a lot of the other approaches. I've also done some work in outdoor environments. This was kind of pre, you know, Oculus Quest, where you have outward facing cameras and can kind of track anywhere. So we set up GPS fencing and did some inertial foot tracking. And, you know, we actually put the grocery store out in a very large field where we could do really, really low imperceptible rates. My favorite study outdoors that we did was like a 2-kilometer walk where we just had, you know, sent people down a straight path and wrapped them around in a, you know, 22-meter radius to kind of match, you know, the recommendations from Frank's work. And lately I've been doing a lot with artificial potential fields. So this is kind of a different approach where instead of trying to get people to the center, get people to an orbit, or, you know, draw people towards something, we're kind of repelling them instead. So we want to push people away from the walls and we want to push people away from other users. So this was kind of a really neat way to get multi-user redirected walking, where you could have several people in the space at once. And again, they can kind of walk wherever they want and they just push away from each other and naturally spread out into open space and push away from the walls. And this approach is really good too for odd spaces, right? So, you know, if you think of steering people towards the center, steering people towards an orbit, right? It's basically a circular pattern that you're just sticking into a rectangular room or a square room. But using artificial potential fields, you can actually take advantage of really odd spaces, and any open space becomes viable for, you know, sending people into the wings of an L shape, for example, or, you know, taking advantage of whatever corners are available and spreading people out. So that's been kind of the focus of my work. And I know Evan Suma has done a lot of that with his lab as well, and he's up next. Okay. Thanks, guys.
Okay, let me just share my screen. Okay, hopefully that's visible to everyone. All right, thank you. I'm Evan Suma Rosenberg from the University of Minnesota. Prior to 2018, I was a research assistant professor at the USC Institute for Creative Technologies, where I also had quite a large tracking space that allowed me to do a lot of fun redirected walking research. First thing I'd like to talk about, though, is something a little bit different. It's already been alluded to, Frank mentioned, but one of the philosophies that's characterized a lot of my work has been sort of looking at what people are doing and then coming up with something wacky and different. And so I actually was in the audience in Tabitha Peck's talk on distractors back over 10 years ago, and I had this kind of crazy, wacky idea about how to do something similar to redirected walking without actually using redirected walking techniques, at least not traditional redirected walking techniques. And this led to the development of what I call change blindness redirection, which accomplishes the same goal of trying to walk through a large virtual environment in a limited physical space, but doing so by modifying the actual geometry of the virtual world. You can see here what happened as they walked into this corner here in this original experiment we did. The doors actually move behind their back. And we do this all in various different ways in the environment, move things around behind their back outside of the field of view. And turns out this is very effective and shockingly effective, actually. I was not expecting that. We run this with multiple experiments, 77 people, only one person noticed this illusion was occurring. So pretty powerful. This led to some interesting experiences, such as when we trucked about 1,000 pounds of gravel into the lab and laid it out in a 30-foot long walkway that you could walk along and then use change blindness. I'll skip ahead here just a little bit because it's a long video. And you can see here that the actual door to enter the house was here, and then it moved all the way to the opposite end of the roadway, essentially allowing you to step back out onto the gravel pathway and reuse this mixed reality haptic walking surface. And we can do this because these change blindness techniques are a little bit more discrete and predictable than other redirected walking methods. Moving on, this actually then led to kind of other types of interesting mind-bending illusions, such as impossible spaces, which looked at self-overlapping architecture, sort of you can imagine rooms that are bigger on the inside and adjacent to one another. We've done a number of experiments that have indicated that you can actually do quite a bit of this. Some of the numbers that we found was 50%, over 50% overlap in square footage before people can begin to detect that these illusions are occurring. And Niels Nielsen has actually recently presented a paper this year that showed with the presence of distractors, this number can jump up even dramatically more. You get a lot more bang for your buck in terms of these spatial illusions. The following year, Christina Vasileska did a internship in my lab over the summer, and she generalized this to what she called flexible spaces, which is this twisty hallway illusion. You can kind of see here these hallways that kind of are algorithmically generated to go from room to room and kind of twist back in on each other. Again, no redirected walking techniques here are used. The system just sort of generates these twisty hallways on the fly. And again, it works. It's a really neat illusion. So to summarize that section of work, this really introduced sort of a new class of spatial manipulation techniques, and we actually collaborated with Frank and Gerd to develop an expanded taxonomy for redirected walking techniques. And some of these impossible spacious experiences have actually been built into commercial implementations such as Unseen Diplomacy, which you can actually download on Steam. The second class of work that I'm going to very briefly mention is on redirected walking systems work, similar to some of the work that Eric Hodgson has done. This really came about because Matti Asmandian, my PhD advisee, was really interested in more of the algorithmic side of redirected walking. And Mary actually helped as an outside committee member on his dissertation. A lot of this comes down to how we can predict the user from anything from an open world where you need a reactive technique to things where like what Sharif did, which was more kind of a linear route where you can have static planning approaches. And we've done work in all different categories along this spectrum. I'm only going to highlight very quickly two right now. And this one was actually inspired by techniques from multi-coordinated robotics. I'm not going to talk too much about it because Eric just introduced the idea of artificial potential functions. Coincidentally, at the same paper session at IEEE VR 2019, we also had three papers, one from my group, two from Eric's group, all presenting on similar ideas of artificial potential functions, although we did some different experiments involving resetting, so they were kind of complementary. The other class of work I just want to briefly mention is in the static planning, which is sort of the linear case where you're kind of pre-planning an experience. And what Matty came up with during the course of his PhD work was a combinatorial optimization approach, where you essentially exhaustively compute. If you're going to say, go make a 90-degree left turn and walk, you can actually end up in many different locations depending on just different applications of gains. What happens if you just exhaustively compute for a given virtual environment and physical environment, all the possible combinations, and then just pick the optimal one for that walkthrough? Turns out that this is a combinatorial explosion and is very computationally intensive, but he has a lot of clever algorithmic tricks to be able to handle that. And so his algorithm called Copper, which is in his dissertation, which was recently awarded an honorable mention for IEEE's Virtual Reality Best Dissertation Award. This algorithm can be used to basically map any arbitrary linear walkthrough into the optimal set of gains for a given physical space. Matty also in the course of his PhD developed the redirected walking toolkit, which is mainly reactive techniques and resetters, but that is on GitHub and is free, integrated with Unity and free for non-commercial use. Many papers have used it, and actually I'm getting emails from students now, I think in their final projects, who are trying to use it now. So that's a resource available for the community. And then very finally, because I'm over time, I just want to point to some of our more recent work. This is paper that was just presented last month and won Best Paper at ACM VRST, the work of my senior PhD student, Gerald Thomas, who's currently on the academic job market. Gerald has been looking at alignment of arbitrary and physical environments with redirected walking, essentially using those artificial potential functions, but not just the repulsive forces to avoid collisions, but actually attractive forces to allow you to essentially use redirected walking to align towards a physical target and then allow you to physically interact with, say, a haptic object or something like that. It's a really kind of new and exciting area. Although UNC has done some work on this in the past, these kind of computational approaches to alignment is something I'm really excited about moving forward. And then very quickly, just want to acknowledge all the PhD students and collaborators I've had at University of Minnesota and USC ICT and the funding agencies that supported this work. And then with that, I'll hand it over to the next speaker.
Okay, thank you all. I'm Keigo Matsumoto from the University of Tokyo. It's a great honor to be here among you. And Frank already mentioned the relationship between redirected walking and multimodal. And I'd also like to talk about multimodal redirected walking. So our research motivation is very simple. We want to enhance the effectiveness of redirected walking by using multiple senses. And as you know, conventional redirected walking techniques relied mainly on vision. However, our spatial perceptions consist of various senses, such as vision, vestibular, proprioception, and auditory senses. So we think we can improve the effect of redirection by using these senses. From Earnest sensory integration model, our sensory integration can be explained by maximum likelihood estimation. For example, the proprioceptive and vestibular variance is larger than the visual variance. The combined probability density is shifted towards the visual estimate. We hypothesized this sensory integration model could be applied to redirected walking. So there are two ways of multimodal redirected walking. The first way is sensory matching. This method presents stimuli consistent with visual stimuli to the proprioceptive and vestibular senses. This allows the combined probability density is shifted towards the visual estimate. Here is a study improved ascending and descending sensation by stimulating haptics and proprioception on feet. There are small bumps under users' feet and provide passive haptic stimuli, which correspond to the edges of the stairs in the virtual environment. This allows users to feel they are walking up and down the stairs, even though they are on flat ground. Here is a result of the experiment. The perceived height of deers was higher in the haptics condition, and presence scores were also higher. Here's another visual haptic redirected walking technique called unlimited corridor. Users walk along semicircle walls with touching them, but they feel touching flat walls and walking straight forward. By using this system, we compressed an infinite larger shaped virtual space into a 7-meter square space. The next one is redirected walking using galvanic vestibular stimulation, GVS. GVS can evoke virtual head motion and sway to another current direction by stimulating the vestibular organs electrically. We thought we could use GVS to distribute vestibular sensations to closer depth of vision. It's still in the preliminary stage of the experiment, but the results suggest that the threshold is wider in the GVS condition. The second way of multimodal redirected walking is decreasing the reliability of senses. Based on the sensory integration model, by reducing the reliability of the non-visual senses, such as vestibular or proprioception, the combined probability density is shifted toward to the visual estimate. So here is a study using noisy GVS for redirected walking. It looks very similar to the previous study, but by applying white noise instead of unidirectional currents, we've reduced the vestibular sensations reliability. It's also still in the experiment preliminary stage, but the results suggest that threshold is wider in the noisy GVS condition. So future work, we can still try different multimodal redirected walking methods, such as vibration and electrical stimulation for proprioception. At the same time, we need to start thinking about design guidelines for multimodal redirected walking. So thank you for listening.
Yeah, thanks to all of the speakers. It was really interesting. I think we can have a good overview about the topic now. So I will just start with some questions, and of course you can also come up with questions after this. So like my first question is to Mary, like when you started working on this, or when you're a PhD student, Sharif started working on redirected walking, did you expect that like we would still talk about redirected walking 20 years later, and like and that we still have like so active research on this topic? Like we see like 5 or 6 papers on redirected walking on each VR conference. So
a distinguished member of the Carolina faculty told someone one time, I don't think there are any more dissertations in redirected walking after Sharif. I think that the amount of research, that number of things that turned up on the search was just phenomenal and unbelievable, actually. So it's been very surprising, and I think the breadth and the different directions that the research has gone has been really very gratifying to have taken something that, you know, a student he just thought of it on his own. He thought about flight simulators and how, you know, you accelerate and then you wash out, and how you could apply that to the human being, the vehicle. And look what it's done. It's really very cool.
yeah, yeah, it is. Maybe like, do you think that we will also like see more like 20 years of research on this, or like do you think now it's almost complete?
Well, it's interesting because we have such different resources. because you're able to real-time model the space that you're in, then the problem of avoiding stuff that's in the space, like in your living room, and the whole issue of having multiple people in the same space, I think is still tricky. And we can't predict where people want to go. And so the algorithms have to be able to do the best they can and then anticipate and keep people from running into each other and running into the walls.
Yeah, and I think one of the reasons why I think redirected walking isn't really going away is because it's a popular topic with students. Like, it's just mind-bending and cool. So as long as students want to do it, they'll figure out new interesting things to research.
Mm-hmm.
Yeah.
Mm-hmm. And my 2 cents here, to be honest, it's not solved yet. Yeah. So I mean, we have our experiments, and of course in the Hive, if you have access to like a gym to do redirected walking, it might work. But in my living room, no chance at all. Yeah. And even all the demos that we produced, some of them have a, as Evan called it, a linear route or a very narrative-driven approach to this. But as soon as you really start to freely explore with multiple people, that's not solved yet, and I don't see that it's going to be solved anytime soon.
Mm-hmm. But yeah, that's a good point. But like, I mean, is it even possible, or is there even, or maybe the other way around, which application domains would actually benefit from redirected walking? Because like, if you have a very small room, it does not work because the room is too small. You need at least like a couple of meters to walk around for this technique, and if you don't have them, you cannot use it. But if you have a huge space like the Hive or like a warehouse scale VR setup, then you might even not need redirected walking because you can already use real walking.
Yeah, I can comment on this a little bit. I had a company approach me a number of years ago now, and we ended up not doing the project for other reasons, but it was a really cool application of redirected walking. And the problem was it was an oil refinery essentially, and they did virtual training for the repair technicians, and they did it in a cave, right? So you have to navigate through this maze of pipes and machines and like find the spot in this oil refinery where you need to, you know, identify the part and make the repair and do everything. And one of the things they were really frustrated at with their current training was that the oil refinery is like a mile square, like it's huge. And to get through the maze of pipes, you're just pushing an Xbox controller and like flying through, you know, and it really didn't simulate the real world effects of you just carried a bag of tools for a mile trying to find the place you're, you know, trying to repair. So there's physical fatigue we're not simulating, there's, you know, mental fatigue. So they were really interested in, you know, can we simulate this huge facility and have people actually walking and carrying things over large distances? So I think those kind of applications, you know, really lend themselves well to, you know, we need people to physically walk, we need people to physically navigate. I also see a lot with the gaming, right? So, you know, you mentioned, I can't really do this in my living room with, you know, consumer VR, but, you know, more and more the consumer VR systems are portable, right? So I could go out on a football pitch and turn on my, you know, my inside out tracking, and now I have a massive tracking area, right? You know, I think one of the big limitations now is when you set up your safety bounds, it's a very small area, but, you know, I don't think there's too much of a reason you couldn't have a much larger safety bounds and redirect within that, you know. And obviously there's a lot of like outdoor sensing and finding obstacles and finding other people. So I think there are really interesting entertainment applications and industrial applications and a lot of really cool stuff you can do with this.
Yeah, Frank also wants to.
Yeah, another application area I would like to comment on, and I haven't really thought about that when starting on redirected walking, is also for therapeutic applications. So we collaborated here with our clinical partners for treating people suffering from Parkinson. So typically they have some asynchrony while walking. So they have one leg, which is typically shorter than the other one. And here one of my PhD students, Omar Janet, used a mapping of the one leg to increase the step length of this leg compared compared to the actual step length. And it actually helped. Yeah? So after some couple of minutes, like 10 minutes or so adaptation, Parkinson's disease people started to actually walk longer with the other leg. And I think that might also be interesting, just thinking about completely different applications in which redirected walking could be beneficial.
And people forget about redirected walking in place, which Sharif did in a cave. And it was a four-sided, so 3 walls and a floor, and they rotated it around so you faced the front. So that might have helped in the oil rig. And an architect swore that that they closed the 4th screen. So that was very effective. But that is interesting in pulling in the highly realistic walking in place, another unsolved problem, and mixing it with redirected walking.
Yeah. Maybe another related question from Gerd, he wrote it in the chat. He wrote, like, thinking about students looking for a PhD topic related to redirected walking, where do you think is the most need for future research? Better algorithms, integration of machine learning, better understanding of human perception, integration of haptics, multimodal feedback, applying the theory to practical uses. What do you think about this?
Those are all great areas. I mean, I think the algorithms we have, you know, the improvements I've seen over the last few years are more at the margins than, you know, I think early on we were growing in leaps and bounds and making big performance gains. But you know, I think now we're getting slightly better algorithms. I see a lot more potential in kind of the combining of things, right? So like Keigo's research, you know, can we take the known techniques and then like layer in this extra thing that buys us something new? And I think that interacts a lot with the applications, right? Because I think a lot of what is the best technique really depends on what you're trying to accomplish and what the context is and what the physical area is. And so I think there's a lot of really interesting work there. The machine learning is really interesting too, of like, you know, there's so much we can do if we can predict better and kind of get better understandings of where people are going to go and those kind of things. And so I've seen some really interesting things with machine learning lately.
The other thing I would like to add here is, of course, it's super interesting to redirect users while walking, but users also want to interact. And one of the ideas, I think, which also evolved from Mary's lab by Love Cooley's work, was using redirected touching as well. So not only redirect the camera, but also our own body parts, as I mentioned in the Parkinson's disease with the legs, or as Love did with redirected touching as well. And having a good combination of redirected walking, redirected touching, or putting my body parts in a redirected way for some application might also be interesting.
A couple other thoughts would be, and I think Eric mentioned this a little bit, in that the kind of consumer VR systems are sort of moving outside the lab. And one of the really things that's interesting is that we're getting more devices with integrated SLAM, right, which can now map environments on the fly. And so moving away from this idea of these sort of like sterilized, like rectangular spaces that are completely empty, and moving into the real world use cases. Like maybe I can't use redirected walking in my living room, but maybe my entire house has quite a bit of walking space, but it's irregular. And being able to sort of navigate in these types of like unconventional environments, I just feel like the more that as more consumer SLAM and tracking technology advances, we're seeing more VR in the wild, and redirected walking could be used in the wild, but there's a lot of safety concerns. And so research at the intersection of the physical environment, redirected walking, and specifically user safety, I think is sort of still a wide open area. And then the other thing, I was hoping I'd get a chance to do this because I never like to be on a panel without saying something controversial. And so one of the things that I think that really we need to understand better is sort of individual variability in thresholds and adaptation, possibly long-term effects. Longitudinal studies are extremely rare. And you know, it's great to have kind of like average guidelines of like sort of thresholds, especially I loved Frank's chart of sort of the average radius decreasing over the years as technology changes. But all of my experience, I've seen some people can do way more and be totally comfortable. And some people, you know, even a small amount of redirection, they find nauseating. And so we need a better understanding of not just individual variability, but individualized ways of being able to measure that efficiently and being able to understand for an individual, how do I quickly understand what I can and can't do so I don't make you ill? I think that's still a very, very wide open area that needs work.
Yeah, maybe because you just mentioned Frank's slide with the different detection thresholds that increased over time. Like, Frank, do you think that there is like, or where is the limit for this? Like, if we would have the perfect display in the future, like.
Yeah, I don't have an answer, but this was, of course, my thought when making this graph and seeing if it kind of approximates a certain value at some point. So this graph I made was just looking at the number of pixels available. We made some calculations by taking a look at the effective pixel, so by also incorporating the field of view, but that was not really helpful here. I'm not sure, but from just what we experienced so far with some of the demos, I think there is a limit at some point, and I think we're really close to this limit, what we can actually achieve with even very good head-mounted displays. So by just using gains, I don't think that we will have a situation in which we can guide users on a radius which is smaller than 5 or 6 meters or something like this, because then the sensory discrepancy will just be too large so that people can't notice. So I think that will be the limit. So we can't solve redirected walking in living room, at least not in my living room, with only using gains. So there must be some other approaches here, like the ones that Evan introduced or Keigo.
That's been my experience as well. I remember in the forest study we did, I put a decimal place in the wrong point, you know, during one of our pilot studies, and we were steering people on a 2-meter radius instead of a 20-meter radius. And you know, that lasted for 1 or 2 participants, so we figured it out. But I mean, they were just remarkably unsteady on their feet. They were trying to follow the curves, and it was just, you know, way too tight, and they were, you know, looked like they were drunk essentially. So I think there is a physical limit of, you know, you push it too far and it just becomes disconnected, and it doesn't feel like there's a relationship between the visual and physical stimuli. So.
Keigo, you oh, sorry.
Oh yeah.
I would just note that there might be some habituation over time, though, that people might be able to habituate to some degree, and we don't necessarily know how that those sensitivity changes as they get exposure. Sorry to cut you off, Keigo.
Yeah, I just wanted to ask Keigo, because like you presented some stuff on multimodal VR and like haptic redirected walking and auditory redirected walking. Like, do you think which approach is the most promising one?
Yeah, I think the proprioception is the most promising, because previous studies of attitude control have shown the vestibular sensation detects relatively slow movement, whereas the proprioceptive sensation detects sudden movement. And I think in redirected walking, sudden movements are much easier to notice than slow movement in general. So I think the method of lowering the reliability of proprioception is a more promising approach.
Yeah. Sorry, I want to ask another question to what Evan just said, but I forgot it. Sorry. Can't remember, but something else that I wanted to ask, like all of you, maybe, I don't know who can answer this, is like, or maybe you already answered it, but my question was like the current steering algorithm, they cannot prevent you or the user from colliding with the wall. Doesn't matter how large the space is, it can still happen that you collide with the wall. Like current algorithm cannot help there. So you still need some kind of like stop sign in the application and reorient the user so he turns around and is facing the tracking space again. Like, do you think that we can solve somehow in the future? But maybe you already said that, like, yeah, the key is in combination of different techniques, and maybe this is also the answer to this question.
One of the things we don't know is how annoying it is to actually be aware of what's going on. So can you insert a noticeable rotation just to get yourself out of a corner or from hitting the wall? There are some people who said, you know, particularly if you're in an application that's scientific visualization and your data is not a room, who cares if you notice a little bit of rotation? Now, unless it makes you sick. I think that's an interesting thing to think about.
Yeah. Yeah, actually, I remembered what I wanted to ask Evan, or say to Evan's comment. Like, you said that there might be some kind of adaptation or habituation to redirection. And I think there was also a paper about this 1 year ago. Frank was a co-author on this. It was from Markus Lappes' group, right?
Yes, so what he did in this experiment was basically an adaptation for like 10 minutes or so towards, again, to one side only. Yeah? And of course, there is some adaptation if you continue to walk in circles in the same direction, but he has never changed the direction. Yeah? So the adaptation only worked in this case if you walk always on the same curve to the same direction. Yeah? And there is, of course, some adaptation, but I assume this kind of gets lost once you change the direction. But on the other hand, I also agree to Evan. Of course, it's the more you work with redirected walking, at some point you kind of get adjusted to this manipulation and better understand it. So it's more like a usability kind of thing. You still notice that you get manipulated, but you know how to compensate also this sort of manipulation. But still, this is a very limited area in which we can further decrease the required radius, for example.
Yeah, I was definitely more thinking about sort of more long-term habituation and adaptation. You know, just some of that's motivated by my own anecdotal experience, having been doing this now for over a decade. And, you know, when I'm in VR all the time, and some of it's perceptual, right? You know, I get cybersick easily, and that hasn't changed so much. But what has changed also is in the way that I move in VR. I've actually trained myself to move in such a way that makes me less sick, and then I can also tolerate things like redirected walking more. So I think it's a really interesting question, and we just don't have long-term data on that because VR has not been at the scale it has been in the last few years. But now there is an opportunity, especially now that people have VR in their homes and we need to do remote VR studies in people's homes. Maybe this is an opportunity for the students out there to do some of these studies.
Mm-hmm. Yeah, I have one last question from my side is, so there is already so much research on redirected walking, and we already agreed that there is still a lot of research to do in the future, that this technique is not like completely researched, but since there is already so much work done in the past, you would assume that there are already a lot of VR applications using redirected walking, but at least I don't know of so many. So why do you think it is like this? Like, I mean, Evan mentioned this game on Steam, or I just forgot the name, but Unseen Diplomacy, which uses some impossible spaces. But except of that one, I don't really know many more games, entertainment applications, or any other application that make use of redirected walking. So is the technology not there yet? Will there be more in 5 or 10 years? Or is it just maybe also a matter of communication? Is it like only in the research bubble and the practitioners out there just don't know how to apply this technology? What do you think?
I think some of it's the game industry's attitude towards cyber sickness. They're very, very conservative about wanting to do things that could potentially make people ill, right? That's why teleportation has been so widely used, even though it's a very tedious and not many people enjoy using it as an interface. So things that have a risk of making people sick, if you're trying to sell the maximum number of game titles and hardware that you can, you're going to be risk averse, right? So that's probably a good reason why it hasn't made in a lot of applications. One that has been successful in public installations, though, is the Void, which is probably the most well-known example of that. There's actually a Void installation at the Mall of America here in Minneapolis that uses redirected walking.
Yeah, I'd say the space constraints too, right? Like something like the Void, where you can set up a controlled physical environment. You can have the space you need. The examples that Keigo were showing, where you're installing railings or walls, those don't really lend themselves to consumer-sized tracking spaces in your living room, right? Like that's where the market's at for the game industry right now. And until we get to a point where, again, you go out and play in a field, go out and play in the park, and somehow we've sorted out the safety issues, I would expect to see it continue to be very limited in consumer spaces and more just towards arcades and installations.
In Japan, non-gaming company actually interested in this kind of techniques, such as like a real estate, and also have some big factories. Maybe they want to walk through the, I am not sure, but their real estate or the factory, of course, virtual factory.
Yeah. Okay.
Eike, there are some questions in the chat, just to let you know, in terms of you have overseen that.
Oh, yeah, I've overseen them. So, so who started it? Oh, that's a lot. Okay, this is, yeah, from this one. Gate analysis while applying gain could be an interesting approach to explore. This is not, yeah, it's more like a comment than a question.
I think then Kyle's question would be
Kyle's
the next,
question, yeah.
the influence of avatars.
Can the panel comment on the influence of avatar and the mapping of avatars to tracking data and the success or failure of redirected walking?
So maybe I can comment on this. That's really a good question, Kyle. And I think in particular, due to the larger field of views that we actually have nowadays in our head mount displays, we're actually able to see our own body. So it seems to make sense actually to use the avatar and also redirect and manipulate the avatar to further improve redirected walking techniques. Also, I think having agents, for example, as potential involvement of distractors might also be very nice, because we are very good in understanding how to prevent occlusions with other natural human beings around us. So I think we will probably see more of this in the future as well.
It gets to be an interesting problem too when you talk about multi-user redirection, because the people who are physically in the same space as you might not be co-located with their virtual representation. So I've always found that to be an interesting research area, and especially too when you talk about like preventing physical collisions, where someone's avatar might be well away from you, but you're about to physically walk into them. I've seen some applications where it's like you temporarily show a ghost in their physical position, so you don't have to do any fancy algorithmic like figuring out where to put people. You just kind of show a ghost and you naturally step around them and kind of sort it out on your own. But yeah, I think this is a really ripe research area, to be honest. There hasn't been a lot of work done with avatars and redirection.
Yeah. Okay. Next question from this chat is, COVID seems to have an impact on the development of VR as a kind of a driver of digitalization, for example, remote working. Maybe an estimation from the panel on the overall development of VR in the upcoming future.
Well, I guess it is kind of an indication that we're meeting on Zoom and not in hubs, right? I think we're heading in that direction, VR being a pretty viable team interaction technique, teaching technique, remote delivery, remote training. but and I feel like the pervasiveness of the hardware is not quite there, where, you know, I can't teach a VR class and expect all my students to have VR, even though some of them might. And we're pretty far from, you know, 5 or 10 years ago when I know none of them have anything, right? But yeah, I mean, COVID has had a really strong impact on the way we work and the viability of VR. And I don't know, kind of curious to see where it goes in the future.
At least from my personal experience, so I think as many of you, we spend like 10 to 12 hours per day in some sort of Zoom meetings with all these gallery views. And in the first lockdown phase, my research group decided to make some VR meetings using Mozilla Hubs, similar to the IEEE VR conference that we have used. And I really enjoyed this. So really being able again to see like body language, having this idea of a shared space together, knowing from where people are talking, etc. So as Eric said, all the hardware is still too bulky that I actually want to use that for 10 hours per day during my working hours. But I also hate to use Zoom and these two-dimensional gallery views. So I'm really looking forward to have more feasible, better technology and having a shared experience together with people in the same room rather than with these gallery portrait views that I'm currently seeing.
Okay, thank you. So there are some more comments in the chat. People are like recommending games with that are using impossible spaces. One is T for God. I tried this. This is a really good one. So yeah, also my recommendation, try it. I don't know the other one, the second that is recommended, but I think there are no open questions anymore in the chat, and we already, yeah, 6 minutes into the break. So I think we close up now. And there's still this Discord server where you can also ask questions afterwards. And yeah, some of us will be available there answering the questions. And yeah, I really enjoyed this panel. Thanks to all of the speakers. It was a pleasure to discuss with you and meet, even if it's like only virtual on Zoom and not even in VR. But yeah, I hope to see you all again soon, and thank you very much.
Thanks, everybody. See you.
Thanks for hosting this, Eike.
Yep.
Thank you very much for the invitation.
Thank you.